All right, so here we are for day two. Starting here with the homework question from the previous day. Um, Actually, I wrote it all out this time, so I'm more prepared. Woohoo! I'm learning. So let's see how we're kind of going through this just to make sure we're all on the same page, figuring out what to do for this question. So we have the mass of the Earth and the mass of the Moon, and we're given the mass of a proton and the mass of an electron, and we're trying to figure out what the total charge of the Earth and the total charge of the Moon would be, given that the Earth is entirely made of protons and the Moon is entirely made of electrons. So we know from up here what the charge of one proton and one electron are. So if we can figure out how many protons and how many electrons would make up this Earth and Moon, we could then figure that out. So let's start with the Earth first. So Earth, we have the mass of the Earth, 5.972 times 10 to the 24. And we're going to divide that by the mass of one proton. After all that, so that would then give us, okay, how many of those protons do we need to get to that mass of the Earth? So if you divide this, 10 to the 24 divided by 10 to the minus 27, so that's subtracting the exponent. So 24 minus negative 27 gives us 10 to the 51? Yeah, 10 to the 51. And then the coefficient part, so 5.972 divided by 1.67. Okay, and I'll round to here. So 3.576. 3.576. So that's how many protons there would be to make up the Earth. So therefore, the charge, the total charge, would be that many protons times the charge of one proton. So 1.6 times 10 to the negative 19. So again, exponents, you're multiplying it now. So 10 to the 51 times 10 to the negative 19. So 51 minus 19 gives you 38. Yes. 38 coulombs. And it's going to be, whoops. And then we multiply that. So we have 3.576 times 1.6. So I'll just do 5.72. So we have 5.72 times 10 to the 20, 10 to the 38 coulombs as your charge of your proton Earth. And just to specify, to be as clear as possible for these, since it's a positive charge, that I just want to put the plus in front of it. Okay, I know that of course that's a positive number, but it's good to just do that just to make sure you're 100% confident and you know exactly what you're going at. So, okay. Then, same thing, but now with the Moon. So now we have the mass of the Moon, which is 7.348 times 10 to the 22, divided by now the mass of an electron, so 9.11 times 10 to the negative 31. Okay, exponents, 22 minus negative 31 gives you 10 to the 53. And then you got to find the coefficient, so 7.348 divided by 9.11. I'll do 0.8066. 0.8066. Okay, so that's not in correct scientific notation though. So we want to multiply the coefficient by 10, so like that, and therefore this goes from 53 down to 52. Okay, that's how many electrons you have, which means that your total charge of your electron moon would be this many electrons times the negative charge of an electron, which gives you, let's see, 10 to the 52 minus 19, that would be 10 to the 30. Wait. This is totally wrong. What did I do? I was like, wait, what did I do? Why did I say 10 to the 38? I'm stupid. Okay. 42. No, 30. What? I can't math. Oh my god. Okay, 51 minus 19. Okay, 32. Jesus. I'm being ridiculous. I was like, what's going on? Okay. So then 52. Okay, that'd be 33. Okay, I don't know why I was totally derped on that one. Whoops. Okay. And your number here is going to be 8.066 times 1.6. So I'll do negative 12. So it's 12 point negative, right? But now this again, it's not in correct scientific notation, so we want to change this to 1.29, which means this is going to become the 34. Okay, that's correct. This is correct, not 38. What was I doing? I'm being ridiculous. So here are your numbers. Here's your positive charge of your proton Earth, and here's your negative charge of your electron Moon. Now, this number is like 20 times bigger, but that's because even though the Moon is like close-ish to 100 times smaller in terms of the mass of an electron is like 2,000 times smaller. So there's going to be, therefore, about 20 times more electrons to make up the Moon than protons to make up the Earth, which means the charge you're going to get is about 20 times bigger. So that's why that lines up in that sense. So, okay, enough of that. So you should see kind of how this works again. I'm sorry I messed up out there. But we're going to move on to our new stuff today, which is, you can see here, electric fields and electric forces. Okay. Now, here's the deal with electric fields and electric forces. Yesterday's thing was pretty straightforward in terms of here's electric charge, it's positive or negative, and also has a numerical value, which is represented by coulombs. Okay, so that's fine and good. Now what do we do with it, right? Okay, we have charge, but what does it actually do? What's the point? So this is where electric fields and electric forces come in. Okay, so here's your warm-up question to kind of get this started. What other interaction have we already studied that involves objects affecting each other even when they're not touching each other at all? Okay, so we can have objects that are completely separate from each other, there's no thing connecting them in any way, but they're affecting each other in some sort of manner. And there's actually multiple of these that are there, but there's one of them that we've really already looked at. Okay, so pause this, think about it for a bit, and see if you can figure it out, and then come back to this. Okay, so the one that we've looked at already, again, an interaction between things that we don't have, or that didn't make any sense. An interaction between things that they're not touching at all, there's no physical actual connection between them, but there's still an interaction. What is it? And again, we've already studied this. Gravity. Gravity is an interaction between objects. We've definitely already gone over that, and it's some sort of invisible interaction. It just seems like, hey, there's nothing there, but there's clearly some sort of interaction going on. And that's sort of a hint from what I talked about yesterday with how I was saying how charge creates electricity, just how mass creates gravity, right? It's the same idea. And again, I'm keeping this link between electricity and gravity because it is an important link, and you'll see why later today, mathematically, how it actually lines up with gravity really nicely. So there's other things you could put here. For example, magnetism is a connection between things we haven't seen, which that'll be later in the unit. And there's also like subatomic stuff, like if you know about like the strong nuclear force and stuff. There's other things like that too. But the one that we've actually studied is gravity. So that's what we have there. Okay, so now what? We have charges, but what do they do? So this gets into electric fields. Now, I could just sort of jump straight into electric forces, and I find that when I was taught physics, everyone always just jumps straight into electric forces because, again, there is a very nice connection with the gravitational forces that we've already done. So people are like, oh, look, this connection, it's so neat. And it is neat, but I feel like then going backwards then to electric fields from that is like way more confusing than it needs to be. So I'm going to start with the electric field. Okay, so the idea of an electric field is that any charged object creates an electric field around it. Okay. In the simplest case, the field emanates outward spherically. Okay, I was going to say radially, but again, it's three-dimensional space. So this is actually, think about this kind of similarly to wave intensity. Okay, so remember, wave intensity, we had like the intensity of the wave equals the power divided by 4 pi r squared. Okay, this is what we had for the wave intensity. Where you have here's a thing producing a wave. Again, we usually talked about it in terms of sound, but it works for anything. Here we have a thing that's producing a wave, and that wave is then spreading out as a sphere, and in all directions, and we can sort of measure like the strength of that wave, given how strong the wave is, but also how far away we are from it. Okay, so this is a very similar idea conceptually. You have a charged object, and instead of emitting out a wave, it's emitting out this electric field. Now, again, the field is invisible. You don't actually see. Don't think of this as like actual lightning shooting off of the thing. That's different. But it's something that you can't see. But again, it affects things. Okay. We could actually have done this when we talked about gravity. We could have talked about gravitational fields in the same kind of way, but it's not really talked about too much, and so the electric field is more important because it also does link to other things as well, whereas the gravitational field, it sort of just talks about the force of gravity, and then also when you get into like general relativity stuff, that's like, then it's kind of linking how this idea of a gravitational field links to like curvature of space-time, but whatever, that's not important right now. So, what we do have, though, is this electric field. So there's two kind of questions about the electric field. The first question is, how do we measure it in terms of like a number, right? How do we get a number for this? And conceptually, what does it look like, right? So in terms of an equation, well, it is actually kind of similar. And I didn't even realize this until just yesterday when I was thinking about this. It is actually kind of similar to this equation, this wave intensity equation that we've already done. Because let's think about this wave intensity equation and what we have in it. So we have the power, right? The power, and that's sort of the energy, right? It's the actual thing producing the wave. How much oomph does it have? Okay. And so similarly, we're going to want something that has some sort of oomph to create this electric field. And well, what is that? Well, it's the charge, right? The charge determines the electricity. So the charge is sort of creating this electric field. Now, I forgot to kind of mention this earlier, but the symbol for charge in terms of like a formula is a lowercase q. Okay, that's kind of how, I know it seems kind of weird, but q is charge, okay, in coulombs. So when you see that there, that's your charge in that sense. Okay, so we have this thing creating the electric field, and it depends on the charge. And then they have this idea that it's spreading out as a sphere. Okay, now that still is true. Okay, so just like how with wave intensity, the electric field spreads out like a sphere. So you think, okay, 4 pi r squared, so it's kind of the same thing. It actually is very similar to that, except we do something a little bit different. So the r squared is still the same, but 4 pi, that's just a constant, right? 4 pi is 4 pi. It's not going to change depending on anything else. And so what they did is they sort of absorbed the 4 pi into another constant. Okay, and so instead of having a 4 pi, we instead have a different constant that's just k. Okay, so while k is known as the, well, pretty straightforward enough, it's the Coulomb constant. Okay, because again, all this stuff involves coulombs. So, and instead of I here, we're actually talking about the electric field strength. Now, this is kind of annoying because there isn't really a good letter to describe electric field strength because we've used up all the letters already, kind of, that would be helpful. The one I use, and the one that I usually see, is E. Now, that's not the best letter to use because we usually use E as energy, and this is not energy, okay? So the electric field strength is not an energy, it's not a joules number, it's actually newtons per coulomb, and this will make more sense later, but that's kind of the number it works. And but again, like, what else letter should we use instead of E? Well, electric field, I mean, field is an F. Okay, but then it's like force, right? And we're going to get to, right? We're going to deal with forces in a bit, so we can't use F. So E is kind of like the next best option, even though it's not that great of an option. So just remember that E, capital E like that, in this unit is the electric field strength. It's not energy. So we have this equation here that describes the strength of an electric field. It depends on the charge of the thing and the distance we are from that charged object. The Coulomb's constant, what is that? It's actually pretty easy to remember. It's 9 times 10 to the 9. So, yeah, pretty straightforward in that sense. Actually, you notice that's actually a big number, right? We're kind of used to constants usually being small numbers, right? Like, think about what are the recent constants we've used. The Planck constant, that was the h, that was like negative 34. The gravitational constant from last semester was negative 11. So this is actually a pretty big one. It's 9 times 10 to the 9. This is rounded. It's like 8.98 something, but close enough. So, yeah. Oh, and then r is your distance from charge in meters. Okay. So let's actually see how this works. Let's do an example of this. Okay, so let's say, example, find the strength of the electric field. I don't know, let's say 3 meters away from a 10 microcoulomb charge object. Okay, let's do that. And let's say plus 10. Okay. So, we want the field strength, so that's E. So it's going to be KQ over R squared. So what numbers do we have? Well, K is just the constant, 9 times 10 to the 9. Let me put all these in parentheses just to kind of separate them out so it's a little bit easier to see what I'm looking at. Okay, so then Q is your charge. So we have 10 microcoulombs. It's positive 10, so we have then 10, and it's micro, so that's 10 times 10 to the negative 6. Which therefore, since it's 10 times 10 to the negative 6, this is just going to be 10 to the negative 5. That's your charge. And then divided by the distance squared. So we have, 3 meters away. Yeah, so then it's 3 and it's r squared. So it's 3 squared. Okay. So this ends up being, let's see. Whoops. You're just multiplying these exponents together. So we have 9 times 10 to the 9 times 10 to the negative 5. So this is going to be 10 to the 4. And then, so then we have 9 times 10 to the 4. However, that's just divided by 3 squared, which is 9. So this ends up actually just being, well, 10 to the 4. And the unit is newtons per coulomb. So that might seem like a lot, right? Electric field strength of 10 to the 4, that's 10,000. The electric field number is usually fairly large. And that's often because of the Coulomb constant being 9 times 10 to the 9, right? So just how I said your Coulomb numbers are usually going to be pretty small, like 10 to the minus 6. Your electric field numbers are usually going to be pretty big, like 10 to the 4, 10 to the 5, 10 to the 3 maybe. That's kind of your range for the electric field number usually. But it can also be in like the millions or so also. So again, talking about macroscopic objects, we're talking about protons and electrons, then it can be a little bit different. But don't be surprised if your electric field number is kind of large. So that's how that works there. So then, now also you may notice, okay, well, wait a minute. The charge can be positive or negative. So how does that work, right? And mathematically, it's the same, right? So if I find the strength of the field, and if it's a negative charge, it's also just kind of the same idea. In terms of the math, it's all the same. The only difference is I would have, if this was a negative charge here, then it would be, what's the difference? I just have, that's a negative, which means multiplying that would mean this is a negative. Oops. And you'd get a negative answer. Now, but what does this mean? What does a negative actually mean? Well, when we've dealt with negatives before, I've usually had negatives dealing with direction. Okay, think back to vectors, stuff about like forces and momentum. Positive versus negative. What was the difference? The direction. That's the same thing here. So, here's what this looks like. Okay, so remember how I said that the shape of the field and how it kind of comes from the wave intensity, it looks like a sphere. Okay, a sphere that kind of spreads out from your charged objects. This is where the plus or minus comes into play. So, the shape of an electric field around a lone charge. Okay, so this is just one charged object separated from any other charged objects. Just that one charged object. It's that field is spherical. Now, you can draw this. You can sort of draw this electric field. using radial lines coming from the charge, okay? And I'll show you an example of this in a second. But there's one more thing. Is what direction are the lines? Are the lines coming out of the charge, or are they going into the charge? Okay, and so here's where the positive or negative comes into play. A positive charge has lines going out of it, and a negative charge has lines going into it. Okay. So this is where the positive and negative comes into play. So let me show you an example what this looks like. Okay, here. So here we have three objects, positively charged object, a negatively charged object, and a zero charged object, in which case there's just no field, so there's nothing. So here, they're all radial, right? You have these radial spikes kind of coming in or out of your charge, but if it's a positive charge, they're all going outward, and if it's a negative charge, they're all coming inward. Okay, that's the difference. So when we go back to the question here, find the strength in electric field 3 meters away from a whatever charge object. The electric field amount is a vector, so we need an actual direction here. Now here's the thing, I don't give you a direction, I just say away. So this is actually not a really great question. What I should have said is maybe what's the strength of electric field 3 meters, let's say, to the left, let's say, of that charged object. Okay, so let's think about this. So when we solve a question like this, what you should really do first is just ignore the negative. Okay, just ignore the negative in the charge. Just ignore it. So we don't have that, we don't have that, and we don't have that. Okay, so that's our strength of our field. Then it's best to kind of draw this out, and it's hard to do on a computer, but if you have this on a piece of paper or something, think, okay, what does the field from this charged object look like? Well, it's a negative charge, which means its field is going to look like this. So if we are to the left of this negative charge, which direction is the field? To the right. Okay, the direction of the field is in the direction of the arrows. So this is where we have to kind of think about this. So the full answer would be 10 to the 4 newtons per coulomb to the right. And this you have to be careful, right? Because, for example, if I switch this question and I say, what is the strength of the electric field 3 meters to the right of a negative 10 microcoulomb charge, then numerically it's exactly the same, right? Instead of right over here, I'm over here. So the difference is not the number. The difference is that now the field is pointing the other direction. It's still pointing towards the charge, but now I'm just over here instead, so it's pointing to the left. And then conversely, if I change this to then say, oh, well, what if it's a positive microcoulomb charge? Again, the math is the same because I said to kind of ignore the negatives and positives for the actual math. It's still 10 to the 4 newtons per coulomb, but now if I'm to the left of a plus 10 microcoulomb charge, I'm over here. Now the field is pointing to the left. Just realized I spelled it right wrong because I'm smart. So that's sort of the thing about this you have to be a bit tricky about. Don't just kind of stick in the negative and think, oh, boom, negative, I'm done, I know what's going on. No, you have to really think about the direction. You have to think about the direction. You have to think about how this works together with not just the charge that you have creating the field, but where you are in relation to it. Okay, so again, I could have said, what about 3 meters above the plus 10 microcoulomb charge? Okay, if I'm above it, then which direction is it going? It's going up. Okay, so that's the direction I need. So you have to be careful about this. And this does matter, okay? This is not just some it's some arbitrary thing because, we're uptight and we have to make you do extra work. No, this is actually legitimately matters in terms of figuring out how things work from this. So this is really important in terms of getting this straightened out. Now, next question is, what if how can you sort of differentiate charges? For example, okay, here's a field from a plus 10 microcoulomb charge. What if I had a field from a plus 20 microcoulomb charge? Right? What's the difference? So the difference is that the number of lines drawn from the charged object relates to the strength of the charge itself. Okay, so more lines equals a greater charge. And by greater, I mean like in an absolute value sense, right? So if I have a negative 10 microcoulomb charge versus a negative 20, the negative 20 is going to have more lines, well, I guess going into it in that way. So an example of this is kind of like this here, right? So, and it doesn't have to be equal. So, for example, if I have a plus 10 microcoulomb charge, that doesn't mean I have to draw out 10 lines. You should like at minimum draw 4, but you should probably do like 6 or 8, just to be have at least some consistency. But so, for example, if this was a plus 10 microcoulomb charge, this is twice that, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so this is 8 lines, this is 16 lines, which means whatever the strength of this charge is, it's going to be twice the strength of this charge. Okay, so it's proportional, right? And so you can see how that kind of works there. And this is probably 32. I don't want to count it all. So this would be twice that as well. So for example, if this was plus 10 microcoulombs, and it is plus, right, because all of the arrows are moving away from the charge. So if this is a plus 10 microcoulomb charge, this would be plus 20, this would be plus 40. Okay, and that is a way of kind of telling you how strong that is. And one other way to think of it is like how, for each little piece, so let's say within this piece right here, how many arrows are there, right? There's, of course, a lot more arrows here than within this piece that's like right here versus, this piece right here. And also, you'll notice that as you get further away, the arrows are getting more and more spread out, again, showing that, like, they get, they sort of get diluted out as you go out into the world. So that's kind of how this works here, and it kind of shows the strength of it this way. So that's all fine and good, and you might think, okay, I mean, radially moving out, just have to keep in mind about this kind of stuff. Not so bad. And that's true when you have a charge by itself. So, if you have multiple charged objects, their fields interact with each other. Okay. They don't just ignore each other and pass through each other like nothing happens. They interact with each other, they interfere with each other. So, here's sort of the rules for this. And again, these are sort of broad rules, and I'll show you some examples of how this works. It's hard to really get, like, especially if you're drawing this by hand, like a really concrete, like, oh, this is exactly what it looks like, because it's, a little bit of fudging about how this works, but I'll show you some examples and kind of get this through. So here's the rule. If you have 2 charges that are either both positive or both negative, okay, either one, the field lines bend away from each other. Okay, so they bend away from each other. And I'll show you what this looks like in a second. If you have 2 charges that are of opposite sign, the field lines bend towards each other. And towards each other and connect, by the way. So let me kind of add that in there. So here is what this looks like. This here. Okay, so here we have 2 positive charges, and normally, see, they're all kind of trying to come out radially, but they end up bending away from each other. Okay, so they bend away from each other like that. Now, and here you have a positive and a negative, they bend towards each other, and you can see the positive lines end up connecting into the negative lines. Okay, so you can kind of see how this works. I really recommend, like, just kind of Google imaging, like, electric field lines, and just kind of seeing how they interact with each other. Because it is kind of weird, but if you kind of stare at it for a while and you see a bunch of examples, it helps. These dotted lines, by the way, are sort of representing, like, along this dotted line, the field strength is, the same as to whatever it is. So what this can, by the way, then the question is, well, what is the field strength, right? What is the actual number in these examples? Well, it depends. Well, so what you need to do is find the electric field strength from both of these charges. Okay, so let's say I'm in the middle here. Okay, let's say I'm in the middle here. I want to find what is my field strength from this charge. Okay, let's actually do that. So let's go to an example and say, okay, let's say you have 2, I'll just say 1 microcoulomb charges to make the math easy. 2 positive 1 microcoulomb charges that are I'm gonna make this math really easy. That are 2 meters apart. Okay, they're 2 meters apart, and then find the electric field strength halfway between them. Okay. Now, we have to do this one at a time. There's the rapid question. Okay. So we have to do this one at a time. So let's do for the first one. So the first charge we have, so say E1 equals, again, K Q1 divided by R squared. Okay. So again, K is the same. 9 times 10 to the 9. It's going to be times the first charge, which is just 1 microcoulomb, so that's just 10 to the minus 6. And then divided by the distance squared. Now, they're 2 meters apart and you're halfway between them, so you're 1 meter away from this charge. So, the 1 squared is just 1, that kind of doesn't matter. 9 times 10 to the 9 times 10 to the minus 6, so that becomes 9 times 10 to the 3, which is just, 9,000 newtons per coulomb. But we have to think about which one is this, okay? Which direction is this field? Let's say the one on this first one is the one that's on the left, right? We have 2 charges. Let's say this is the one that we've been looking at so far is the one on the left. Therefore, if we're here, the field would be coming out of it. So therefore, this field is to the right. Okay, and let me just to save space, I'll do the arrow thing. There. Okay, so it's to the right. Now for the second one. Now, you may be able to pick up what kind of answer we're going to get here. This is still the same. And this is still the same. And again, since we're halfway between them, this is also still the same. So everything is the same, which means we're still 9 times 10 to the 3, or 9,000 newtons per coulomb in terms of our strength. But now, this charge is the one over here. Okay, this charge is the one over here, and we're again here. So which direction is the field from this one? To the left. That's not to the left. That's to the left. Okay. So get off the screen. Okay. Whoops. All right. So then the question is, what is the total field strength? You add them together. And again, you have to think about the directions. So E total is going to be basically the 9,000 to the right and the 9,000 to the left. So what's the total? 0. You'd have 0 field. Directly in the middle, right? If I was not directly in the middle, then if I was over here, for example, then this charge would have a slightly stronger field than this charge, which means I would have, I don't know, let's say, instead of 9,000 for both sides, let's say I'd have 10,000 from this one and 8,000 from this one. The 10,000 is pushing me to the left. The 8,000 is pushing me to the right. Therefore, my total would be 2,000 to the left. Okay? So you have to kind of treat this sort of like how we treated forces in terms of adding forces together. It's similar in that sense with this here. Okay? Now, you'll notice, okay, what if I did this exact same question, though? So let me copy this. But instead, you have a +1 microcoulomb charge that is 2 meters away from a -1 microcoulomb charge. Okay, so now all I've done is I've changed so that one of the charges is positive and one of them is negative. Okay, let's just base it off of this image here. Okay, so let's say the positive one is on the right and the negative one is on the left. Then if we're halfway in between, what do we get? Okay, so now notice the only thing I've changed is that one of these is now a negative. So the numbers are the same, right? So actually, I'm just going to copy these because you'll actually get the same numbers. But what's the difference? The difference is that, let's look at the signs. Okay, so let's say this one is E1. Again, let's say that's the one from the left. Okay, E1 is the one on the left. So therefore, which direction is the field when I'm in the middle? Well, since this is a negative charge, the field is pointing to the left. It's pointing to the left, which means that this one, not to the right, it's to the left. Now the E2, the positive one, again, I'm here. It's coming out of the positive one, so it's also pushing me to the left. So both of these charges are to the left now. Let me just have a little bit of space here. So both of these are to the left, which means what is my total field? Oops. 18,000 newtons per coulomb to the left. Okay, and you should be able to kind of see that from this image, right? So comparing these two, right? Think about how, again, the field lines. If I was perfectly in the middle, like I could keep drawing field lines, right? But they curve away from each other. So if I'm perfectly in the middle between these two charges, there's never going to be a field line that gets to me because they're all bending away from each other. However, here, right in the middle, I'm always going to get field lines that are going through me, and they're all kind of bending sort of in toward the middle here. And you can kind of see how, like, these lines sort of like get like closer and closer together, the dotted lines do, and that's sort of telling you that like the dotted lines basically tell you like as you go through these dotted lines, the numerical value changes. So as you get to the really tightly packed dotted lines, they change a lot, so you get a big number here. So you can maybe see how this can get very complicated. And we are going to kind of work through practice of this and just seeing how this works as we go over, through next couple of days. So if you're still like kind of, oh, this is a lot to take in, I know it's a lot. Okay, I know this is a lot. This is sort of the meat of the first half of this unit, and it is a lot. It is rather difficult to kind of keep all this together, but we're going to practice this multiple times. So don't think about like, oh my god, if I don't learn it today, I'm not going to, it's too late. No. But I also want to show you a couple other examples of what these can look like. So here you can see, and also now here, this is when the strength of the fields are all different, right? Notice the number of arrows coming in or out of these are not the same. So you can see kind of how that comes into play, right? So both of these are positive charges, but this one is a stronger positive charge, right? There's more lines coming out of it than this one here. So if you think about it, if you were halfway in between these two charges, it wouldn't be 0 because this one is stronger. So sure, maybe if you're halfway here, maybe this one is 1,000 newtons per coulomb, but this one is 2,000. So if you're stuck in the middle, well, it's not gonna cancel to be 0. You would have to be closer to the weaker one for it to cancel out to be 0, right? And conversely here, same kind of idea. These are both negative charges. You can see the lines kind of coming in there. Also, you have to be closer to the weaker one for it to cancel out to be 0. Now here, you can see, again, a positive and a negative, where the positive has much less charge than the negative one, and they're all kind of coming in. There's all this, more coming out around here. So you can kind of see, and again, positive is a lot more than negative. You can see how that works there. And also, of course, you can also have more than 2 charges. Now, we're not going to deal really with, I think there might be one question to make you deal with this that's annoying, but I want to see if you, but mostly, like on a test or something, you're not going to have fields where you have charges that are not in a line. Okay, now you could have charges that are in 3-dimensional space, right? And that makes things incredibly difficult to figure out. We're not going to really worry about that, but we might have to worry about something like this here. Okay, so again, here's your sort of normal charges by itself. Here's your standard positive charge to your standard negative. And here you can see, here's where the positive charge is a lot more charge than negative. It sort of overwhelms it. Now, in this kind of example, you can actually get a really interesting situation where notice how these lines kind of come in on the side, but then these ones sort of go out that way. So what this means is that you can actually be like over here and have a total electric field of 0, right? Think about this. So you have, let's say you're being pulled inward by the negative field, the negative charge, and because you're pretty close to it, but it's kind of weak, so it could be, I don't know, again, like 1,000 newtons per coulomb going in towards this charge. However, the positive charge, you're a lot farther away from it, but it's a lot stronger, so you could have a 1,000 newton per coulomb electric field from this charge pushing you outward, but you're all the way out here. So in that way, you have 1,000 pushing you outward from the strong positive charge, 1,000 pulling you inward from the weak negative charge. It could cancel out and be 0 when you're like out here, okay? So notice that there is no way that if you have a positive and a negative charge, there is no way that you can have a 0 electric field if you're between the two charges. But if one of them is stronger than the other one, you can have a 0 situation when you're actually outside of them. Okay, so that's kind of weird in how that works, but that does come into play. Now here's an example of 3 of them. Here is 3 positive charges, and so you can see there's these sort of 0 points here. This, though, I don't know if this actually work as cleanly, because even if you're over here, you are still getting affected by this charge as well. So you'd have to be very careful and mathematical about like balancing this perfectly. Also, just notice based on the lines, each of these three charges are different in terms of their strength. So you can imagine this can get very, very complicated. So again, even with all of these complications, these are all just in straight lines, right? I could, if I could maybe form these into like a triangle, that would be one thing. And then again, even then, they're still on a two-dimensional plane. You can turn them 3D, and it gets ridiculously complicated. So this gets very, very complicated. And we're going to spend time on this, really kind of working through this. But this is sort of the introduction to everything that we got to deal with here. Okay. So that's everything with electric fields. But we still got electric forces. So now, thankfully, once we have the field down, the force is pretty easy to get to. Okay, so here's how this works. When another charged object is in an electric field, it experiences an electric force. Okay, so you have the charged object that's creating the field. Okay, you have that charged object creating the field. You might have multiple charged objects creating fields, right? And they're all interacting with each other and interfering with each other and all that kind of stuff. But then you then put some other charged object into this field. That charged object is sort of interacted with the field, and it feels a force. So, and how this works is that the force on a charged object equals its charge times the field strength. Okay, so F is the electric force on charge on I'll say on what's adjectives I use? I'll just on new charged object, because again the key is well, hold on. So Q is the charge of new object, and E is the electric field strength that's there. Okay, so in other words, you have an electric field. It's created by a charge. It's doing its fieldy stuff. Okay, it's doing all that. You do all the math. You do all this kind of stuff, figuring out what is the total field strength, blah, blah, blah. You do all of this work. Then you say, okay, I put some new charge into this field, and it feels this force. Okay, so going back to... let's go back to this example. Okay, let's say we found the field strength between them. We found this here. So from this question, I could then say... here, I'll label this example B. Okay, so... and let me go... so this was example B. I'll say this is example A. Okay. That all... crud. You know what? I'm gonna bad grammar just to keep the spacing nice. Okay, there. So here's the example. Okay, so you put a 0.5 microcoulomb charge, and I'll say it's a positive 0.5 microcoulomb charge. Halfway between the charges in example B, find the force this new charge feels. Okay. So what we have is, we know what the field strength is halfway between those two charges. That's what we found. It was this here. Okay, so E equals 18,000 newtons per coulomb to the left. And now we have this new charge, which we're putting there, which is 0.5 times 10 to the negative 6 coulombs, which is, in other words, 5 times 10 to the negative 7 coulombs. And the force is therefore, well, Q times E. So 5 times 10 to the negative 7 times 18,000. I don't need the units yet. So, what math is that? Well, we have 5 times 10 to the negative 7. So that times 18,000. 0.009. That's your answer. 0.009. That is the force that this feels. This new charge would feel once you put it in that field. And again, this field was based off of this here. Okay, so if we found the field strength halfway between these two charges, it was 18,000. We now plug a new charge right in here. What is the force that it feels? 0.009 newtons. Okay. Now then the next question, okay, but again, force is a vector, so we need direction also. And you're thinking, oh crap, another direction they have to worry about. This is where all the field stuff kind of comes into play, and what makes this the whole dealing with the field stuff and why we draw the lines and have the arrows, why we do all of that. This is what makes it more helpful, because here's the rule. Positive charges follow the electric field lines, while negative charges do the opposite. Okay, so this field was 18,000 newtons per coulomb to the left at this position, which means this force is 0.009 newtons to the left. And think about this for a second, just conceptually, okay? Again, this is our example, and we put a positive charge right here. Well, which way is it going to go? It's going to go away from the positive charge and towards the negative charge. It's going to go to the left, towards the negative charge. Conversely, if this was a negative charge that I put right here, it would do the opposite of the arrow, in which case the negative charge would want to go towards the positive charge. Okay, and so far this seems pretty basic, but again, go back to an example like this over here, where if I maybe told you, what if I have a charge right here, which way is it going to go? Right? Is it going to be pulled inward towards the negative? If it's a positive charge, you could think, well, it's going to be pulled in towards the negative charge. But wait, this really strong positive charge over here, maybe that overpowers it and pushes it to the left. That's where you got to kind of do the work with the electric fields and figure out, what is my strength of my electric field at this position, and what is the direction in total? Therefore, when I put my new charge in there, which way is it going, right? Is it following the lines, or is it going the opposite of the lines? Okay, and so it really just takes practice getting this down and just kind of getting used to how this works and making sure everything comes together. So in almost all circumstance, I would recommend to kind of just find the electric field strength, do the work, and I know that this is kind of annoying and there's a lot of stuff to worry about for this, but then once you have the electric field, it's real easy to get the force, right? You just multiply by whatever this new charge is, and you get the force. Now, there is a shortcut, okay? For example, if you just have two charged objects. So if you have two charged objects and you just want to jump straight in to finding the force between them, you can do this. Okay. Think about the formula we had up here. Force equals Q times the field. Okay. F equals Q times E. Well, remember, what is E, right? What is our electric field equation? Because we have Q times KQ over R squared, right? And now remember, these two charges are different, right? One of these charges is creating the field. The other charge is the other one. It's not doing that, okay? So therefore, we want to separate these charges. So we have K times Q1 times Q2 divided by R squared. So this is a way of just jumping straight to force if you have two charges and you want to know the force between them. Now, you can sort of like, you can just use this to sort of figure out the force between any sort of charged object. I don't recommend it unless it's very specifically that example, because I think it's just unnecessarily complicated. And the field, I think going through the work for the field is generally safer to do, and it works better in that sense. So be really mindful about that. But there is something that's interesting. Okay, so this is our electric force equation if we have two charged objects that are a certain distance away from each other. Now remember, from last semester, we had a different equation that was finding the force between two different objects based off of gravity. And I'll try to line this up nice. It was that force was G m1 m2 over r squared. You can see now how it's kind of the same. Okay, the electric force has the same kind of equation as the gravitational force. So the gravitational force, you have the mass of the two objects, the distance between them squared, and a constant. For the electric force, we have the charge of two objects divided by the distance between them squared times a constant. It's exactly the same form of equation. And this is why I think a lot of times people start with this force equation. They start here and then try to say, okay, we have this force, now let's like divide out one of the charges to get an electric field. And it's like, but wait, which one are you dividing out? And it's like, I don't think that's helpful to start that way. I think it's a lot more helpful to start with the field and go to the force. But this is why they have this connection. You can see how this could be important. So that's sort of my sense there. This is why this looks the way it does and how this kind of works. And this is why I've been kind of giving you sort of these conceptual hints about how think of electricity like gravity. And this is why. The formulas for the forces are very, very, very similar. So just keep that in mind, and I'll label this gravity and I'll label this as electric. Okay, so you can see how that works there. Let's see, is there anything else I want to point out? Again, this is a lot. I totally acknowledge this is a lot. I know that. Again, we're going to be practicing this for a while. So I know, but this just really comes down to practice. It really does. And getting used to this, and yeah, this stuff, it's a lot. It is. So I fully acknowledge that, and that's why this is one of the reasons I've said this unit is probably the hardest one for most people, and the electric field stuff is a big reason why. I think that's everything though. Let me double check my notes, see if there's anything I'm missing. Nope. Okay, that is everything. So let's move to the wrap-up question. Up here. What? Okay. Oh, that's annoying. Anything I can... Here, I'll take off that line. There, looks a little bit better. Okay. So, here's your wrap-up question. Calculate the electric field strength created from a plus 5 microcoulomb charge when you're 2 meters to the right of it. What direction is the field? Okay, so I'm just having you find the electric field strength, not worrying about a force. You have a plus 5 microcoulomb charge and you're 2 meters to the right of it. What direction is the field? Okay, so pause this, think about it, work out the numbers, get a direction, and come back when you have that. Okay, so we need the electric field strength, so we're going to use the equation for the electric field, kq over r squared. What do we have? K, again, is 9 times 10 to the 9. We have the charge that's creating the field, so that's the 5 microcoulombs. So 5 times 10 to the negative 6. And then that's divided by the distance squared, 2 meters to the right squared. So what do we have? Okay, so we have 10 to the 9 times 10 to the minus 6, that's 10 to the 3. And we have 9 times 5, so that becomes 45 times 10 to the 3 divided by 2 squared, which is 4. So 45 divided by 4, I'm lazy and I'll just do the thing. Okay, 11.25. Okay, so this becomes, I always do that, 11.25 times 10 to the 3. Now that's not in correct scientific notation, so I should have that as the correct, which would be 1.125 times 10 to the 4, which if you want to just write that out as a regular number, is 11,250 newtons per coulomb. Oh, by the way, this whole newtons per coulomb thing, now you should understand why it's newtons per coulomb, because the force here is just, well, the force is the newtons per coulomb, the electric field, times another charge, which is just a coulomb, right? So I have newtons per coulomb times the coulomb, I get newtons, right? So that's why the electric field is newtons per coulomb. So anyway, so that is my electric field strength, but what direction is it? I'm 2 meters to the right of a positive charge, okay? 2 meters to the right of a positive charge. So here's my positive charge. I'm 2 meters to the right of it, which means my field is pointing to the right. So this will be to the right, like that. That's your answer. Okay. You got some homework questions. You got 2 of them this time, and again, they're, more to do than the one that we had before. Let me find where they were. Oh, there they are. Here's your homework questions. So we have a proton and an electron that are 1 angstrom apart. Now, an angstrom is just a fancy way of saying 10 to the minus 10 meters. Okay, so that's the distance between them. So draw the electric field lines. Again, I guess you can't really do that on the Google form, but it's good to have it at least for reference, so you can kind of, again, even if the question never asks you explicitly to draw the electric field lines, you always should, just so you have an idea of kind of what things look like and where the directions are going. So at least on a piece of paper, draw it out, and you can see how that works. So then, what is the strength of the electric field created by the proton at the electron's position? Okay, so in other words, I'm saying the field that's created from the proton when you're the electron distance away, what is that strength? Okay, so the strength created by the proton where the electron is. Then, what is the electric force on the electron? Okay, so then I'm saying, okay, you found the field created by the proton where the electron is, so then what's the force on the electron? Okay, and then explain why this is the same as the electric force on the proton. And you should explain this kind of mathematically, why this works the way it does, okay? And hopefully you should kind of see how that works based on the formulas up there. So then, and this kind of gets into what we go from here, the mass of the proton is this, mass of the electron is this. What is the acceleration of the proton? What is the acceleration of the electron? Okay, so again, going back to what we did back in Unit 2, force equals mass times acceleration, right? So once you have a force, you can then find an acceleration, and you can see how that works from there. So sure, the force on the electron is the same as the force on the proton, but because their masses are very different, their accelerations are very different. So you see how that works there. Okay, so 2 is then we want you to use the charges of the proton Earth and the electron Moon that we calculated from yesterday's homework. Okay, so if you want those solutions, check the solutions. I should probably just, well, I'll show them here, wherever they are. Here, okay. So here was your charge of the proton Earth, and here was your charge of the electron Moon, including the negative there. Where am I? Okay. So calculate the strength of the electric field created from the Earth at the Moon. Okay, so the Earth is the one that's creating the field, and you want to find the strength when you're at the Moon's position, and then here's the distance between the Earth and the Moon, this many meters. Then, do the reverse. Find the strength of the electric field created by the Moon at the Earth. Okay, so again, now the Moon's creating the field. What is the one that the Earth feels? And then what is the force between the Earth and the Moon? Okay, so you can see how this works there and work through this stuff that way. So again, this stuff, it's kind of a lot. We're going to be practicing it and see how this works for there. Going forward. Now, tomorrow, I have a simulation lab. Okay, it's a simulation lab on electric fields. Hopefully it's something that can help you sort of visualize things better, and just kind of mess with things and see how they work. Okay, so hopefully that will maybe put this in a bit better perspective, because right now you're probably brain fried and like, oh my god, this is so much. I don't even know how long this is. I'm kind of afraid to look. This day is probably one of the most heaviest days that we have for a while. So sorry, but that's how things go. Anyway, that's what we got. Of course, you can ask questions in the comments for the classroom post. You can join the Discord and ask me questions there. And I can maybe explain something a little bit more specifically if there is a specific issue. Also, don't forget to submit questions for the random science Q&A thing. I will be live streaming that Friday. And again, I'll give you a link and a time when we get close to that. And yeah, see what you can do with this. I know it's a lot, but kind of forms the basis of everything we're doing going forward, at least for this first half of the stuff before we get into circuitry. So yeah, that's it for now.